For those who missed class today, I'm going to go through and try to answer all the questions for you here from the last exam. I think that would be a good way to actually study for the final exam, is to actually go through, and maybe this will help with the test reasoning, which is a key element that a lot of people are lacking right now, is going through and having some reasoning with these organic problems. Bear with me, I've never done this before, so this is a new thing. So here, problem number 1, we see here an aromatic compound, a purine base, and here the question is asking for which one of these is most basic. You see here in the case of nitrogen number 1, the lone pair is on a sp2 hybridized nitrogen. Here it is sp2 because it is surrounded by 3 electron groups, the lone pair, which is not shown right here, the bond, and then the double bond here. The lone pair is in a sp2 orbital, and the way that we know that is because the p orbital right here is occupied by the double bond. And so this is the reason we don't count that lone pair towards Huckel's rule with the aromatic ring. Over here we know we count this lone pair, not shown, now it is, towards Huckel's rule. We have 2, 4, and then once resonance occurs, 6 pi electrons here for that particular lone pair. The reason this is important here for the basicity of the nitrogens is this lone pair here is not a very basic lone pair, because it is actually cyclizing around the ring. Right here you see it just moving around. So that's a lot more background information than D here, the right answer, provides. If a lone pair is not readily available on the nitrogen, it will not be very basic. On number 2 here, we have the tropylium ion, and here the tropylium is actually aromatic. Each of the atoms in the ring is sp2 hybridized, and it is completely conjugated, which is the important thing, that each one of them here is sp2 hybridized. The carbocation creates that position there that is sp2 hybridized. Normally the tropylium would not have a plus charge, but once it is plus charged, it is completely conjugated, and we have 2, 4, 6 pi electrons. Since it is aromatic, it's going to be much more stable than any of the structures here. A is not anything other than a secondary carbocation. C here, sorry, this is the rough draft, but C here was a tertiary carbocation, and D is actually an anti-aromatic carbocation. So this D is the least stable of all of them, since it is anti-aromatic. And again, anti-aromatic means that it has all the first 3 criteria of an aromatic compound. It's cyclic, it is flat, all the atoms of the ring are completely conjugated, meaning they're all sp2 hybridized. And instead of following Huckel's rule, again 4n plus 2 for Huckel's rule, instead of that it follows 4n here equals to the pi electrons here and then here. Number 3 here may have been a bit tricky. Right here we have a set of carbonyl compounds. All of these CO double bonds here are carbonyl compounds. They are ketones. And the question is asking for the dipole moment. The dipole moment is based on the electronegativity of the oxygen, but that is similar in all of these here. The other thing here that affects the dipole is the resonance. All ketones will have resonance. So here, for example, with B, this is acetone. The resonance structure for that is this here. That is a natural resonance. This is a less stable resonance structure, since this one has more bonds and it also has a full octet on every single atom. That is the most stable resonance structure. Well, that resonance is going to be more pronounced in D here, because once that comes off of there and we gain a positive charge on this carbon here, I'll show it as a partial positive charge there, that actually creates a aromatic compound which is much more stable than the carbocation that formed over here. So since it is so stable, the negative charge is going to want to remain on, a little bit more so on the oxygen than in the case of all these others actually. And that will create a bigger dipole moment. On A here, it's just the opposite. If this comes up and we have resonance and we form a partial positive charge right here, that's going to actually create a anti-aromatic compound, and that's going to be very unstable. Okay, number 4 right here. 4 is a basic question about the carbocation stability. Another way of phrasing this question here is which one would form the most stable carbocation, and that one would be the one that forms the fastest. So let me draw these here individually and show you the most stable carbocation that forms in the reaction. Here we have a reaction, just kind of illustrating this. Here the reaction with the HCl. It reacts with this one here because this is going to be the most stable carbocation. Here you see you pick up a positive charge on a tertiary carbon, and then we have resonance like such. Here the resonance structure shows that is on a another tertiary carbon. So here in class I said a handy way of doing this is kind of adding these up, and we can say this is like a 6 substitution, even though that's not possible. Let's see what would happen if we reacted this other one, this other pi bond here. If we reacted that one there, we form a carbocation. One other thing to remember is that the carbocation is always going to form on the inside carbons to have resonance. So those 2 carbons there. So there the carbocation forms on a secondary, and then once we have resonance, it comes over here. The positive charge is now on this primary carbon right here. So again, if we add this up, primary plus the secondary is a tertiary. So you can see, comparing these two right here, the top one is the most stable carbocation. And we do the same thing for the other 2 here. Let me draw those out. I'm going to do this a little bit faster. Here, if this one reacts, it reacts with the second one right there, and that one will produce a tertiary carbocation here. Tertiaries are going to be some of the fastest carbocations to form. And if we reacted this other one, it would form on the secondary carbon. We don't want that to happen because it's less stable. So that comes over here in the resonance form. This is why it's important to draw these quickly. Here we have a tertiary right there and a primary right here. Do a little bit of math. And we see that's like a quaternary type substitution here. So, but that is less than this one over here, so this is going to form slower than the other one, the first one. And let me do this last one here. I'm just going to show the carbocation here on this last number 3. So here we see a tertiary carbon right here. I'm not going to react this one here though. In order to put the charge on that tertiary, I'm going to react this first one here because this happens. Get the plus charge there, and then resonance is what leads to the tertiary carbocation. But it's actually a composite again of the tertiary and the secondary both. Here's the secondary carbon right here, and then resonance will put the tertiary right there. Tertiary carbocation. Add those up, we get 5 right here. Now we have the ranking. The first one here, which is 6, is going to be first. Then 3 is second. And then we have the next one, the middle one here is the last. This will be third place. So there you see the answer is this one. Another important thing here is you got to make sure that the greater than sign always points to what you're saying is the fastest, or it could be the strongest in some other context. Number 5 is a tricky one here. This one is a problem where it shows you the starting material and the product, and it is asking for the conditions that led to the product. Even though it says it kind of indirectly, it's asking for the product name, but here in the product name you can see these are conditions. These are cold temperatures here with kinetic. Thermodynamic is warm temperatures. Of course, that's both. And then this one here is specifically saying the 1,4 position. The 1 is defined here where the hydrogen added. So this is 2, 3, 4. We just count over there. So 1,4 product would be the chlorine ends up over here on that 4 position. And you can see that's not what happened here. So first off, on all of these type problems, you have to draw the most stable carbocation. Indirectly, it kind of showed you what is the most stable carbocation. It formed after it reacted here on that carbon. So the hydrogen added at here at the end, forming that carbocation because it is resonance stabilized, like such. And the next thing is we notice that the double bond here is not shown right here in the product. It's shown at the end between 3 and 4. So that is actually because here this is the most stable spot for that pi bond because it's tri-substituted. Tri-substituted means we have 1, 2, 3 alkyl groups attached to that pi bond right there. So that's the most stable double bond. And we also have the case here where the chlorine actually added here Let me go ahead and show that mechanism step. This would happen in the case of kinetic, but here, since the pi bond is the most stable here, it would also happen as a thermodynamic product. So in other words, there's no distinction between the two products here. We don't have a kinetic and thermodynamic product. We just have a reaction with the first pi bond leading to both of those. So that's where we say it is both a kinetic and thermodynamic product.